Okay, yeah. So just a reminder that the exam is next Monday. Um, yeah, just take a look at the problems on the PDF. I also got done like the review session in my other class. So if you check the announcements, you'll see like the video that for that one. Oh, you can also find it on the YouTube channel. But yeah, I'll keep the exam similar to the examples we have done in class and the problems on that PDF. So today, the idea was to continue talking about eigenvalues and eigenvectors, which we had started last Monday. So let me remind you what this topic is about. Yeah, there are no questions before we start, right? Everyone is fine. Okay, so the idea of an eigenvalue eigenvector is that you have something that looks like this. So you have a matrix, and you multiply it times a vector, and it just gives you a rescaled version of the vector. So AB equals lambda B, that's the fundamental equation for an eigenvector, right? So that's the name for the eigenvector. Oh, sorry, that's the name for the vector. We just call it eigenvector. And lambda, this number is called the eigenvalue. So what we had done on Monday was just to find ways to how to you find the eigenvalues of a matrix. For the eigenvalues, you have to solve, right? To find the eigenvalues, you solve the equation that the determinant of A minus lambda I equals 0, right? Is that okay? So that is a polynomial. I mean, if you for a given matrix, if you work this determinant out, this will give you some polynomial in the variable lambda, and then you're solving this equation is the same as finding the roots of the polynomial. Of course, in practice, since finding roots is not like an easy task when the polynomial is of degree 3 or more. Usually, the cases like it will give you examples where like it's kind of easy to factorize the polynomial, or the matrix has other properties for which it is easy to find the eigenvalues. But in general, finding eigenvalues just reduces to finding the roots of a polynomial. Okay, that's almost the only thing in this course that we're doing that's not linear, right? Because everything else it means really like that none of the variables are ever raised to a power higher than 1. And today what we have to talk about is how do you find the eigenvectors, which I kind of mentioned before, but I didn't do any explicit examples last time. So for today, like the majority of the time, we just go to this problem about finding eigenvectors. Okay. And the idea is that essentially, if lambda is an eigenvalue, the eigenvectors associated to lambda it's basically what we had. It's basically this equation. It's just that we do the same as last time. You move this to the other side, factorize the b. So you get this equation, which is a homogeneous equation, right? And in fact, this is now this is the following question is related to the midterm. what's the name that we gave to the solutions of a homogeneous system? The set or something as a name. Yeah.
Trivial and then.
It was a null space, yeah. So what this is saying is that the eigenvectors belong to the null space of the matrix A minus lambda I. So that's the important thing, which I'm going to write right now. So the eigenvectors belong to the null space So in fact, the problem of finding eigenvectors essentially reduces to the problem about computing certain null spaces, which we'll do today, but that shouldn't look too different from what in principle you're doing these days to prepare for the midterm. So is that okay? Making sense? Questions up to this point so far, so good? So yeah, let me do some examples to make this more concrete. The first example will be this matrix that we analyzed last time, which was 2, 0, 0, -2. So if you remember this matrix, what it did was it would take a vector xy right, and send it the new vector AB was the vector that is twice as big, right, but reflected along the x-axis. Yeah, this has been the vector we analyzed. I don't know if you remember this one. So what were the eigenvalues for this matrix? They were 2 and -2 in this case. It was easy to remember because like A is a diagonal matrix. Remember that when the matrix is diagonal, the eigenvalues are just the entries of the matrix along the diagonal. Okay. So you just have to call one the first eigenvalue and the other the second eigenvalue. It doesn't matter in which order you call them. Here I'm just following the order along the diagonal, but you know, one is called lambda 1 and the other is called lambda 2. And for each of these eigenvalues, we can find the corresponding eigenvectors. So let's start with the eigenvectors for lambda 1. So you have to look at A minus lambda I. A is 2, 0, 0, -2 minus lambda. Lambda is 2, so it's 2, 1, 0, 0, 1. So when you do this, take the difference between these two matrices, the 2's in the first entry cancel, and then this one just gives you -4. Is that okay? No, I'll just take myself. So now we need the null space of this matrix. So the only thing different from like what you are doing for the second midterm is that for the second midterm, I just asked you to find the null spaces of a matrix A. Now you just have to modify a little bit the matrix A to get A minus lambda I, and you find the null space of that. So we need the null space of this matrix, right? What do you do to find the null space? What could you do? What's the idea? Yeah, good. It's almost good to go. I mean, because this is there's not too much simplifications needed, right? Like if you want, you can put a 1 here for convenience. But that's like what you get. That's how the matrix looks like, right? But again, a null space is a homogeneous system. So what's a homogeneous system here? In fact, like if you wanted, you could also have like changed the rows, but it doesn't really matter to read the system of equations. The first equation just says 0 equals 0, which is not useful information, and the second equation says y equals 0, right? So only the second equation really matters here. And then what would we do once we get to this point? If a vector belongs to the null space, right? Like now you have a vector x comma y. But if it belongs to the null space, it means that y has to be 0. So it becomes x comma 0. And now you can factor out the x. So it gives you 1, 0. So what this is saying is that any vector in the null space is a multiple of 1, 0. So what this is going to say is that 1, 0 is an eigenvector, and any other eigenvector is for this eigenvalue is a multiple of that one. Okay, so let me write that down. So what this is saying is that B1 equals 1, 0 is an eigenvector. And any other eigenvector of lambda equals 2 is a multiple of this vector. Which makes sense because if you remember the actually we had found this eigenvector before, right? If you draw B1 is here, is 1, 0, and A times B1, right? What was A times B1? What it does is just rescale the vector by a certain amount, right? So it's just 3 times as big, right? So what this is like this calculation says is that all the eigenvectors for that eigenvalue are just multiples of 1, 0. Yeah.
Eigenvectors associated with an eigenvalue have to be alpha, right?
No, I'll would take us in maybe 2 or 3 examples. You'll see it may be more than a line. That's not a problem. Yeah, it doesn't have to be lines. Yeah. I'll do a 4x4 case in a bit, and then you'll see it more easily. But yeah, good. Anyone else? Any other questions about this one? So let's do the other eigenvalue. So now let's try to find the eigenvectors for lambda 2 equals -2. So again, you have to do a minus lambda I. A becomes A is still 2, 0, 0, -2. Lambda is now -2, so it becomes +2 times the identity. So this gives you what? 4, 0, 0, 0, right? So we need the null space of this matrix. Again, you just augment it if you want with the column vector 0, 0, and that gives you 1, 0, 0, 0, 0, 0. And this is a system which is easy to solve, which is x equals 0. And 0 equals 0 if you want. But that one is not needed. So you don't need to write any preference. And so if it's x equals 0, that means that if you take a vector in the null space, right? It's 0, comma y. Right? Then you factor out the y. 0, 1. And so what that means is that any eigenvector is a multiple of this one for this eigenvalue. So any eigenvector for this eigenvalue is a multiple of the eigenvector 0, 1. So that makes sense in the picture, because if you look at the picture, if you draw the vector 0, 1, what the matrix does is reflected along the x-axis and double it in size. So if you think what this looks like, where's my, that's the color that I needed. Right, if you look at the vector AB2, that's 0, -2. So it became -2 times, the original vector. So that's why the eigenvalue was -2. So that when the eigenvalue was positive, it kind of points in the same direction as the original vector, and when the eigenvalue is negative, it reverses the direction of the vector. Okay, and what I'm saying is that any other vector that is a multiple of the pink one, the same happens to it, right? It will be reversed and be done like enlarged by a factor of 2. Is that okay? Making things so far so good. Yeah.
Instead of writing it like V1, V2, and then like writing out any eigenvector, can we just write it as like an eigenspace?
Yeah. You could. I'm just trying to write it more in words, but yeah, you can just say, or you could even say like a basis. We'll say later, like a basis for that eigenspace is just that vector or something like that.
So wait, would you have to, you have to specify a new eigenspace for every eigenvalue?
Right. For every eigenvalue, there would be like a null space, and for every null space, there's like a basis, and yeah, it's kind of like that's the only thing that it's a little bit tedious about this process, because it is one per eigenvalue, right? So you have to do this null space for each eigenvalue. So in practice, of course, like the matrices would be like something like 2 by 2 or 3 by 3, so that you don't have to do this multiple times. Or like if it's bigger, it's just that like in the example that I'll do in a couple of minutes, which is 4 by 4, but there are not that many different eigenvalues. But yeah, it's just one for each eigenvalue. You do have to redo this process. But the idea is most of the time these null spaces are kind of quick to find, so there's not that much simplification involved, as you can see from this example. In fact, what I was going to do now, it was like another 2 by 2 case, but it's slightly more interesting than this one, so that you see that it's still not too much of a difference from, like, the amount of time it takes you to find them. Anyone else? Okay, yeah, let's do there was another matrix, another 2 by 2 matrix that we studied last time. So here's another matrix. I have it on my notes. Let me check it. Okay, so last time, this was the example I also did on Monday. We found that the eigenvalues were lambda1 equals 2 and lambda2 equals 3. So those were the two eigenvalues. And yeah, the idea is that for each eigenvalue, you do this thing. So let's try to do it a little bit more quickly. So what are the eigenvectors for lambda1 equals 2? So you have to do a minus lambda I is 1, 1, -2, 4 minus lambda I. Lambda is 2 in this case, so it's 2, 1, 0, 0, 1. And so this gives you what? Gives you -1, 1, -2, and then 2, right? So we have to look at the null space of this matrix. And let me put it down. So we have to look at the null space of the matrix, so null of -1, 1, -2, 2. So you have a method. Well, I mean, you can start, what you can notice in this case is that this second row is just 2 times the first row. So you can just do -2, row 1 plus row 2. Otherwise, it doesn't take too much time to reduce anyways, right? Once you get there, I mean, you can just say that minus x plus y equals 0, right? That's what the system gives you, which is the same as saying that y equals x, right? That's convenient. And so a basis, or like, but what's going to be the null space? The null space would be x comma y is x comma x, right? Because y equals x. So that's x times 1 comma 1. So again, this is saying that any eigenvector is a multiple of the vector 1, 1. So the eigenvector are multiples of B1 equals 1, 1. That making sense? So far, so good. I mean, the only thing that I'm going to say about this is that when I say multiples, I mean, in practice, it doesn't matter too much, but just remember that the vector 0 is not allowed as an eigenvector just for just to make our lives easier. So here, like the multiple has to be a non-zero multiple so that you don't get a vector 0. But besides that, it's really like the null space is really made up out of eigenvectors except for the vector 0. Like the vector 0 is in the null space, it doesn't count as an eigenvector by default. But any other vector in the null space is an eigenvector. Okay, so the only difference between the eigenvectors and the null space is just that one includes the vector 0 and the other does not. But besides that, everything else works as well. Okay, questions about this? But yeah, in practice, you can just say you find the null space, you find a basis for the null space, right? And then you just say the vectors are multiples of the vector, or like a linear combination, which will show up in a second once I do a little. I want this a bit more interesting. So let me just finish this 2x2 case, and then I'll move to the more interesting case of the 4x4 matrix. So now I'm going to do the eigenvectors for that the 2 equals what? 3, right? That's the other eigenvalue for this matrix. So now you have 1, minus 2, or minus 3, 1, 0, 0, 1. So that gives you minus 2, 1, minus 2, 1, right? And then you have to look at the homogeneous system for that, or the null space of that matrix. And again, it's like the rows are the same in this case, right? So you can do minus row 1 plus row 2. And what you end up with minus 2x plus y equals 0. So y equals 2x. Right, so if you take a vector x comma y in the null space, you get x comma 2x, which is x times 1 comma 2. Is that okay? So what that means is that any eigenvector, or just here in this eigenspace, that's actually the name that's given to that. Any eigenvector associated to this eigenvalue is just a multiple of 1. Yeah. Is that making sense? So yeah, let me give you a more interesting example of how this looks like. Where is the, oh, here it is. So how about this matrix? Drop more water, but in the 1 minute or so that will take me to come back, think about what the eigenvalues should be for this matrix, and we will discuss it. What are we talking about?
Since like the matrix is in upper
Mhm.
triangle form, you can just multiply that down the diagonal to get
Right.
permanent, so just do all the diagonals minus the.
Right, right.
And then together, so it'll just be one value of two.
Good. So since it's upper triangle, that's a key phrase. Like this is upper triangular because below the diagonal everything is zero. So yeah, what that means, well, I mean, in practice, if you had done the determinant thing, right, of a minus lambda I, really what you would have obtained is 2 minus lambda to the 4, right? One because there's a 2 for each fact along the diagonal. Or like you can just use this fact that for an upper triangular matrix, the eigenvalues are just a diagonal entries, but it's 2 repeated 4 times. Does that make sense? So yeah, I mean, this is a case where it's kind of easy to find the eigenvalues despite the fact that the matrix is big, just because of this upper triangular property. So it's a useful property to keep in mind for sure. And so the eigenvectors, right? For this lambda, which is the only one, is a minus 2i. Well, but if you think about what that means is that it's subtracting 2 from the diagonal, right? So you just get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Bunch of zeros, like only 2 ones. Is that okay? Is that making sense? Exactly with everyone. So what's the null space? Let me write it this time because we'll need some more space for this thing. Well, in this case, like there's almost nothing. I mean, there's really not much you can do to reduce the matrix. You can just read the homogeneous system immediately. So here, like there are 4 variables x, y, z, and w if you want. So the first equation just says the first row just gives you the equation y equals 0. And the second row gives you what? D equals 0. And then the others do not contribute any information, right? They're just saying that 0 equals 0. Does that make sense? And a vector in the null space will then be x, y, z, w. Right? That's how it starts. But now y you can replace with 0, z you can replace with 0, and you cannot say anything about x and w. Right? So I don't know if anyone remembers at this point what's the idea. Once you get to that vector, what do you do now?
It's split up into that.
Yeah, you split it into the x and w parts, right? And then you can factorize a variable or the parameter. That's also how they are called. Free parameter or free variables. Is that okay? So in this particular example, this is saying that any eigenvector is a linear combination of these 2 vectors. So that actually answers your question because this is actually more of a plane because it's a sum of 2 vectors, right? So in this case, any eigenvector for this eigenvalue of these 2 eigenvectors, like we call them V1 and V2. Is that making sense? So far so good. Uh, yeah,
Let's say we're given like a multiple matrix without like numbers in every single spot, we could just do like the row transformations to get it.
I mean, to find you mean to find the eigenvalues first, or?
Yeah.
I mean, yeah, but you would have to do, I mean, like the annoying thing in that case is that you have to do the row transform, draw operations, not an A, but an A minus lambda I. So that's not actually too convenient because then you have to, you have like this variable in the entries and then you have to start making cases. So like just in practice, it would be, matrices where if you have to do it by hand, like the matrix, like the determinant is just better to do it like by this expansion formula in terms of mini determinants instead of like trying to apply the row operations because of this lambda that's like going to be appearing in the matrix when you do A minus lambda I. So yeah, but that's a good point. Yeah. Anyone else? So what I was going to say about this example is that notice like that this was 4 by 4, right? 4 by 4, but the maximum number of like linearly independent eigenvectors we found was 2, right? So it's not that it is always the case that the size of the matrix goes hand in hand with the number of linearly independent eigenvectors. So for like in the first two examples I did today, that worked, right? We had 2 by 2 matrices, and we had 2 different eigenvectors, like one for each eigenvalue. But in this case, we have a 4 by 4 matrix, and we are only getting 2 linearly independent eigenvectors. So that's unfortunate in a sense, like because of that, this is kind of like a bad matrix. So good matrices will be ones where like, if you are 4 by 4, you get 4 linearly independent eigenvectors. If you are 10 by 10, you get 10 linearly independent eigenvectors, and so on. So like the matrices where this does like there's like a discrepancy, right? Like they don't match up. They won't be as interesting to us for like a reason that will become more clear next time. Okay, but let me make this more write it down a little bit better. The other thing I was going to say, and also I'm about to write this down, is that since this lambda was 4, since the power for this lambda was 4, what that means is that 4 was a maximum number of distinct linearly independent eigenvectors you could have found for this null space. So the dimension of the null space is always going to be less or equal to the power on which the lambda appears, the eigenvalue appears. So let me write those two things down. And then I'll do another example, and then I'll tell you about something else. So, yeah, let's make some remarks. So if A is an n by n matrix, the first thing is that it has at most n eigenvalues, right? That I actually had mentioned last time, but it's good to write it again as at most n eigenvalues. Again, if you were working with imaginary numbers or complex numbers, for those who have seen it, then there would be at least one eigenvalue for sure, because every polynomial has a root in the complex numbers. But since we are working here with real numbers, ordinary numbers, sometimes you cannot like find the roots of a polynomial. So, but the most that you could always find would be n. So it has at most n eigenvalues, and if lambda is an eigenvalue, the dimension lambda is an eigenvalue of A. The dimension of the null space that we have been using computing we will in this case at least be one, that will happen, but at most it will be K. And let me tell you what K is. Where K is the exponent in which to which lambda appears in this polynomial. Okay, where K is the exponent of lambda in the polynomial. So like again, like for example, with this polynomial, lambda equals 2 appears to the power 4. So the K was 4 here. So like what I was saying is that this nullity had to be between 1 and 4. In this case, the nullity happened to be 2, but there could have been other examples where the nullity would have been 1 or 2 or 3 or 4, like it would have depended on the particular matrix. But at least it tells you how big it gives you like a tells you like how big the number of basis vectors would be for these nullities. In fact, I'm going to do another example, but in a second, but that's useful for you to be aware of. So this is a useful, yeah, these are two useful facts, but this is a nice inequality to keep around. Is that okay? Any questions about this? Okay, let's do another example. If I give you the matrix A, let's say I give you that matrix. So what are the eigenvalues for this one? Yeah,
1 and 2.
yeah, it's 1 and 2 because in this case it's actually lower triangular, right? So in fact, if you do this determinant thing, what you will find is 1 minus lambda squared times 2 minus lambda. Okay, so what I'm trying to say is that for lambda 1, for lambda equals 1, the k will be 2 because it's appearing to the power squared. And for lambda equals 2, the k will be 1 because it's just appearing to the power 1. Okay, so what that's saying is that for the first nullity that we will compute, 2 is the maximum number of eigenvectors in the basis that we could find. And for this one, it actually has to be 1 because it would be between 1 and 1. Is that okay? So it is again kind of like it gives you like some sort of expectations to have what number of eigenvectors you should find. So let's try to do this. So what are the eigenvectors of lambda 1 equals 1? again, you have to look at A minus lambda I. Which is A minus I in this case. When you subtract the identity matrix, you get 0, 0, 0, 0, 0, 0, 3, 0, 1, right? And I mean, there's not much simplification that you need to do for solving this homogeneous system. You can just say that 3x plus z equals 0, right? Or z equals minus 3x. That's kind of more useful way to say it. So if you take a vector x, y, z in the null space for this eigenvalue, you get x, y minus 3x. And then we do the splitting thing, the stuff with x and the stuff with y. So the stuff with x gives you 1, 0, negative 3 plus y times 0, 1, 0. Is that making sense? So, what this is saying is that any eigenvector is a linear combination of B1 and B2, right? But what I'm saying, my point is that there could have been at most 2 in this linear combination stuff because the exponent was 2 here, so. Is that okay? And then there's the other eigenvalue left. So now let's look at this eigenvector for lambda 2 equals 2. So you look at A minus lambda I, that gives you 1, 0, 0, 0. Oh, sorry, I am doing this wrong. It's A minus 2I, right? So you have to subtract a little bit, so you get negative 1, 0, 0, 0, negative 1, 0, and then 3, 0, 2. No, it looks fine.
Is it 300?
Yeah, 3, 0, 0. Thank you. Perfect. And then, okay, you look at the null space for this one, like you can, if you want, write it down, although it's not too bad because the only thing you really have to do in this system is like 3 row 1 plus row 3, and more or less after that is kind of straightforward. Right. And so the homogeneous system, like, well, it's like minus x equals 0 or x equals 0, that doesn't really matter. And the other one also says that y equals 0. So the null space is x, y, z equals 0, 0, d, so it's z 0, 0, 1. So again, any eigenvector is just a multiple of that one. any eigenvector is a multiple of P3. Is that okay? Any questions up to this point? Um, Okay, so hopefully this gives you like an idea of how finding the eigenvectors look like, right? So it's just finding a bunch of null spaces. Like you just find the basis for the null spaces basically, and then you're good to go. So now we're moving more into the direction of like using this for something. Okay, so what do you use eigenvalues and eigenvectors for? I won't tell you all today, but we'll do it next time. So for that, we have to talk about, I'll start slow with the case of a 2 by 2 matrix. So that, because again, like many times, if you just understand what's happening with 2 by 2 matrices, you kind of understand everything else. It's just like more computations involved. So, and the pictures are easier to make and a bunch of other things. So let's start with 2 by 2 matrices, and we'll talk about matrices which are called diagonalizable. So that's probably one of the most important type of matrices there are. So essentially, what's nice about these, you'll see next time, is that for these, it's easy to define certain things like the exponential of a matrix, the natural log of a matrix, things like that, which is fun to do. It's actually useful to do also like if you take differential equations, because these linear systems of differential equations can be solved with an exponential matrix, basically. That's all that they are. Um, but yeah, that does require a little bit of slick arguments to make it work. So let's start with a diagonal matrix. So what's a diagonal 2 by 2 matrix? And they will be called D from now on. So if I write like a matrix, the letter D for a matrix, I mean that it will be diagonal. That kind of makes sense. So a diagonal 2 by 2 matrix just looks like lambda 1, 0, lambda 2. Okay. That's essentially all that they are. And why am I calling the entries lambda 1 and lambda 2? Because for a diagonal matrix, the entries along the diagonal are the eigenvalues. Because a diagonal matrix is an upper triangular or lower triangular, however, it's both actually. So like here, the eigenvalues of D are lambda equals lambda 1 and lambda equals lambda 2. Or another way to say it is that this determinant of the polynomial a minus lambda I for a diagonal matrix, it would be D minus lambda I. It would be just like lambda 1 minus lambda times lambda 2 minus lambda. And so it's kind of not too bad to see that those are the eigenvalues in this case. So far so good, everyone with me up to this point. So a diagonal matrix is the most simple, actually of all the square matrices, like the diagonal matrices are kind of the easiest you could think of, more or less. So, let's think about what this matrix does to a vector, a 2 by 2 vector. So if you have a vector v, which is x comma y, what is b times b? That would be lambda 1, 0, 0, lambda 2 times xy, right? And what does that give you? What should I put as the first entry here? Yeah. And the other one will be lambda 2, 1, right? So what does a diagonal matrix does? What does it do to a vector? It just takes the first entry and rescales it by an amount lambda 1, and it takes the second entry and rescales it by an amount of lambda 2. So well, not the problem, but what could happen is that these these entries along the diagonal, they don't need to be the same, right? So the rescaling factor, think about it like it's this diagonal matrix is stretching space, right? So along the x direction is kind of stretching it by a factor of lambda 1, and along the y direction is stretching it by a factor of lambda 2, right? So it's just like maybe the stretching factors are not the same, right? But if I wanted to find a vector that's just being stretched by an amount lambda 1, what could I do? You just wanted it. Or this is a secret way to ask what would be an eigenvector for lambda 1. What should that look like? It would be like, yeah, it should be like, exactly. Let's try to draw it like as a picture. So if you took, for example, just to make it more concrete, if you take the vector 1, 0, right? And you multiply it by the diagonal matrix, the only thing that would happen to that one is the first entry becomes multiplied by lambda 1, right? So this should just be lambda 1, 0, which is the same as lambda 1 times e1, right? So what that is saying is that e1, the vector along the x-axis, is an eigenvector for that eigenvalue, right? So let me write that down. So e1 is an eigenvector for the eigenvalue lambda 1. Is that making sense? And so kind of by like a similar logic, which would be like an eigenvector for lambda 2? It's just 0, 1, right? So if you take 0, 1, which is called the vector 0, which is called E2. Again, like if you take a physics class, it's what they call IMJ, right? Or something like that. But we just call them 1, E2, E3, E4, so on. So if you take E2 and then you do D times E2, right? Well, that gives you 0 lambda 2, which is lambda 2 E2, right? So that means that E2 is an eigenvector for the eigenvalue lambda. Is that making sense? So for a diagonal matrix, what's happening is that one eigenvector is along the x-axis, the other eigenvector is along the y-axis, right? So the generalization of that property, and thus will be the matrices are called diagonalizable, is that in the 2 by 2 case, it just has two eigenvectors which are non-parallel. So let me write that down. So, or let me do the picture first. So a matrix will be called diagonalizable if the following happens. So for a matrix to be diagonalizable, you have like the vector v1, okay, and then which is an eigenvector, and a vector v2, which is an eigenvector also. But it's just that these eigenvectors may no longer be pointing along the x and y axis, essentially. But it is the case that you still have two linearly independent eigenvectors. So let me give you the definition. So 2 by 2 matrix A is called diagonalizable it's called diagonalizable if it has two eigenvectors which are linearly independent. So it will look like this. If it has two linearly independent eigenvectors. So I mean, again, more geometrically, what's happening is that when you have a diagonal matrix, this matrix has two preferred lines in space. One preferred line happens to be the x-axis. The other preferred line happens to be the y-axis. Why are they the preferred lines? Because those are the lines of the eigenvectors, right? So for a matrix, when it's diagonalizable, you still have your preferred lines. It's just that they're not necessarily the x and y axis. So this is kind of like the x-axis for the matrix A. Like this is the favorite axis of the matrix A, the favorite line, and this is the second favorite line of the matrix A. So really, what physically is happening, like, and this actually is a better way of think about it, is that you can start with the x and y axis. Maybe you do like some sort of rotation and maybe bring the lines together, like what's happening in this picture. And if somehow you could rewrite the matrix in terms of this axis, the matrix will look diagonal. So that's actually the way in which you should think about it, is that it's kind of like a more abstract point of view. And because that requires changing coordinates. So if you have like, that's something that sometimes people do in physics classes. definitely it's done like in multivariable calculus or calculus too. If you guys seen like polar coordinates or something of that sort, it's like an analog of that. So there are like ways to change coordinates, and when you change coordinates, it just changes how the matrix looks like. And a matrix is diagonalizable. If by changing coordinates, it would look like a diagonal matrix, more or less. That's kind of the meaning. So, but let me explain that more concretely. That's actually what we will start with next time. So the idea is that you have these two vectors. All right, let's call vector one. What does it mean that it has? So we have these two equations. So we have that a b1 equals lambda one b1, right? And then a b2 is lambda two b2. So the cool, like the insight is to make a matrix whose columns are these eigenvectors. So let's say you define this matrix Q. So what do I mean by this? This is a matrix. This is a matrix whose columns are the eigenvectors. Are the eigenvectors v1, v2. So for example, if v1 happens to have like entries x1, y1, and v2 had entries x2, y2, then what would be this matrix that I'm calling Q? Q would just be x. Let me use the same colors. X1, y1, and x2, y2. So the first column is the first eigenvector. The second column is the second eigenvector. Is that making sense? So you take the eigenvectors and make them into a square matrix, essentially. First vector, first eigenvector, second eigenvector. Now, this is a conceptual problem question. What's the determinant? What can you say about determinant of Q? What can we say about the determinant of this matrix?
So lambda one times lambda two.
Well, that actually that is not so clear. Like I'm asking more. In fact, it wouldn't be the case in general. So what's the important thing about these eigenvectors? That they're linearly independent. So what can you say?
Default rank, so that really.
Is the matrix, this 2 by 2 matrix has to have full rank because the columns are linearly independent. That's another way of saying that the determinant is not zero. Okay, because the columns are linearly independent. Are linearly independent. So another way of saying that is meaning this means that Q has an inverse. So Q is invertible, right? And is that making sense? Let's see how am I going to write this. I always do this. And what we will check next time. So because it's, I mean, it's not like a lot of calculation, but it's better to start it from scratch. Because I already gave you enough information for today. So next time, what we'll see is that, yeah, that's how I wrote it. I mean, that's actually how it works. When you multiply Q inverse AQ, that gives you a diagonal matrix equal to the eigenvalues of the matrix A. So that's in the sense in which this is a more precise way of what we mean by being diagonalizable. So it can be turned into a diagonal matrix if you choose like the matrix Q to be like the eigenvector. So this is like the eigenvalues. Okay. And this actually is like the most important equation, like when it comes to diagonalizable stuff. I mean, that's actually the equation. Many ways, sometimes that's how a diagonalizable matrix is defined. And then you just check that that means that it has like two linear and independent eigenvectors, for example. Well, that's kind of clear. I mean, yeah. But I prefer to start from the perspective of the eigenvectors, and then just check that this will work. So we'll check it a little. I mean, it is the same in the n by n case, but just to make it more explicit, I'm going to do it for the 2 by 2 case. And from there, it would be easy to define the exponential of a matrix and things like that. You'll see why. I'll tell you next time, yeah, how to do that, and then we'll define the exponential of a matrix, the sine of a matrix, the cosine of a matrix, the logarithm of a matrix, the square root of a matrix. Basically, any function more or less like that you would think about can be defined in the diagonalizable case without any thought. It's kind of very easy. When it's not diagonalizable, that it can still be defined, but it is more tricky. So it's not something we'll get into. Okay, but yeah, we'll discuss that next time because it's kind of fun. So. Yeah, I think it's a good ending. So yeah, the next time we will do.